In section 1.5, we're going to be exploring what it means to be a limit of a function. So we're going to start off with our favorite function, y equals x squared. And we want to talk about how to complete the table. We can do this by hand, but we do have the TI technology, so I prefer to go that route. If I'm going to be plugging in x equals 1, well, we'll just do it by hand for this one. I should get the number 1 squared. Now 1.5, let's see if we can use the table feature. So let's pull up our TI. And I already have the graph entered in, y equals x squared. We could do this a couple ways. We could go on the graph itself, and if you were to press trace, you can press the x value that you're interested in. So the next value on the table was 1.5. You could press enter, and it will show you where the corresponding y value is, and also give you the value of that corresponding y value. So that's giving me 2.25. I can continue to press my values of x and get the corresponding y value as well. But sometimes it's nice to see the function, it's nice to see the corresponding y value, but sometimes we like to do this a little bit faster. So I could actually go into the table feature of the TI. If I press second graph, this is going to pull up my table. And I have the table set up so that I ask the TI for every value of x, it will compute a corresponding y value. If you're interested in changing the settings on your calculator for this, you would press second window to access the table setup. And you'll notice when you look down at the independent variable, the ask should be highlighted. So you can use the arrow key to highlight that. And then the dependent variable, which is the y variable, will be automatic. So let's go back to the table. I'm going to press second graph one more time. And I'll enter in all of the values. X equals 1, x equals 1.5, x equals 1.9. You notice the values are coming in pretty fast. X equals 1.99. And I have one of the other values, 1.999. And then let's look at what happens when we're at 2.001, 2.005, and 2.01. Let's see, let's press that one more time, 2.01. And I have a, it still didn't press. Okay, let's try one more time. 2.01, enter. There we go. I do have a value left over from one of my previous problems. Let's just ignore that at the moment with the number 4, but it does give the corresponding y value. So I'm going to switch back to our OneNote. And we're going to fill in our table. So I have at 1, the value is 1. Then I have 2.25, 3.61, 3.9601, 3.996. And then we're looking at 2.01. That's 4.004, 4.02, 4.0401. So the purpose of this exercise is to kind of see what it means to approach something. So I want to kind of have the number 2 in mind. So when x equals 2, I'm going to mark it on the x-axis. We are interested in understanding if the x values are getting closer and closer to 2, we are interested in what their y values are doing. as the x values get closer to 2. So I'm going to look at this in two directions. I'm going to look at coming from x, the negative side, I guess, to the left of 2. So if you're using x values and we're getting very, very close to 2, we're going to see the corresponding y values and what they are approaching. So as the x gets closer to 2 on the left side, you can see that the y values tend to get closer to a particular number. You probably already see what it is, but let's just take our time. And as we go from the other side, this would be the right side. As we're choosing x values, we can find the corresponding y values on the graph, and we can notice that they are getting closer and closer to a certain number as well. And you probably guessed it, as x gets closer to 2, the y values get closer to 4. So that's kind of going to be the theme of our section. Let me kind of write this down formally. And anytime we're talking about limits, this is what we're going to approach. So as x gets closer to 2, the function gets closer to 4. And anytime we're speaking about limits, this is key. You're always going to ask yourself, what are the y values doing? So if you have an idea, as the x is getting closer and closer to a certain number in either direction, we are really interested in seeing what the corresponding y values are doing. Are they getting close to a number as well or not? We shall see. And if we want to speak about this a little more formally, we're going to say the limit of the function f of x equals x squared as x approaches 2 is equal to 4. So there's a lot of writing going on with that statement that we have just discovered, but you might be more interested in some shorthand. So what we would write, and you see it right below us, the limit of x squared as x approaches 2 is equal to 4. So we have limit notation now, formal introduction of what are the y values doing as x approaches 2. So this is actually the definition of a limit. We do have the generic notation, and I'll rewrite it because we do like to speak the correct English for it. So if we're going to say this part in English, communicate, we would write the limit of f of x as x approaches a equals L. I know you all know how to translate the equal sign, but I believe the limit notation is something we don't have too much experience in yet. Maybe a little bit in pre-calculus, but we're going to work a lot with it in this class. So there's an intuitive definition to this. Let me kind of start off with another picture. I'm going to kind of blow this up a little bit. We are kind of looking at, it kind of does look like an x squared. So I'm going to make it a little larger so we have an idea. And we have our function f. And we're going to pick any number on the x-axis. And we're going to call it a. We're going to kind of look at this. So I'll mark it over here. It's any number a. And we're not really going to care at this moment what's happening at the function evaluated at a. So if I were to find its corresponding y value, it's not necessarily our main concern. Kind of depends on whether or not your function's a polynomial or not. There's some interesting parts about it. So before I start, I'm going to try to tell you a little note. We don't necessarily care about the function evaluated at a. We are only interested in what happens to f of x when our x values are near a. So I'm going to approach this the same way as I looked at our concrete example. We're going to look at particular values approaching a from the left. So I'll kind of write a few of them. So coming from this way, we're looking at from the left. And if I were to pick a value over here, and I want to find its corresponding y value, I can mark all the way up to the function, mark where that is, and find its corresponding y value. So it's a little bit over here. We can choose any other value too. We can go a little closer if we'd like. Find its corresponding y value. Mark where that is on the y-axis. So we have some values that are getting pretty close. And if we are looking at what's actually happening, as I pick values of x, and I'm getting closer and closer to a from the left-hand side, it appears that these functions, or I should say these values, these y values, are rising to hit this function evaluated at a, and I'm going to label that L, our limit. So we can take this a little bit further. If you keep choosing these x values, I'll even blow this up a little bit. I mean, as you keep choosing particular x values, finding where they're located on the function, the closer the x value is to a, the higher the y value is, and the closer it gets to the limit L. So I'll write that in English, just in case. Approaching from the left-hand side. LHS is my abbreviation, left-hand side. F of x appears to rise to L. And then we can choose values on the other side. So if we look at a value coming from the right. So I'll pick a value way out here. I'll be exaggerating. If I were to find its corresponding y value, find where it's at on the y-axis, I have a value here. But let me get a little closer. Pick another value, a little bit more. Find the corresponding y value. Find where it is on the y-axis. And you notice that the second value is a lot lower than the first value. And you could keep doing this if you want to. Just kind of for purposes of inspection. We're just trying to see what's actually happening to the y values. So this point, it appears that if you're approaching from the right-hand side, the corresponding y value, f of x, is appearing to drop to L. So I could write that down just in English for formal notes. So approaching from the right-hand side, RHS, f of x appears to drop to L. So the values appear to get lower. So if we have like an intuitive definition, it means we can get f of x as close to L as we want by taking values of x that are really, really, really close to our value of a. So I'll write this down too. It's nice to have in your notes. We have an intuitive definition. This means, one more time, repeating myself, not bad in a math class to do that. We can get f of x as close to L as we want by taking values of x that are sufficiently close to a. So one more time, just so that we can kind of see this, you'll notice as we were approaching a from the left-hand side, our corresponding y values started to rise to get to that limit L. Similarly, if we were approaching from the left-hand side, our corresponding y values seem to drop to get closer to L. So the idea, if possible, we want to get as close as possible to A to figure out how can we get to this y value, this limit. And so eventually, we're going to ask, we want the value of the function to be within 1/10 of L, or we want the value of function to be in 1/100th of L. So what should we pick for our x value so we can get the y value really, really close to L? So that's going to be the idea. And we're going to talk about this in our next example. So we're going to develop this. Be patient, and we'll come up with some new aha moments. So we're going to look at considering the following statement to be true. There we have our limit notation again. And so in English, we're saying the limit of 2x as x approaches 3 is supposed to equal 6. And they want to discover how close must x be to 3 to keep the 2x within 0.01, or that would be 1/100th of a unit of 6. So very, very close to 6. So just kind of remember, when you're looking at your limit notation, the argument of the limit, that's always some sort of function. So it's a good idea if we're trying to explore this, we might want to look at the graph. We'll kind of write this over here. Might be a good idea to graph. And it's not just 2x, it's actually y equals 2x. So I'll just get myself a good idea. That is a linear equation. That is a line with a y-intercept of 0. And the slope is 2x. So we would rise 2 and go over 1. The slope is 2, not 2x. It's the coefficient of the x. We can keep rising 2 over 1 to get more accuracy, especially if I don't have a nice straight edge on my particular graph. So I'll do my best. We'll draw ourselves a line, if we can. Not too bad. But that is our y equals 2x, our function. Now, the next thing I want to kind of talk about is I want to mark where, let's mark where the particular X value in question is. So if I'm really deconstructing this question, they're asking how close must X be to 3? So I'm going to mark where the X equals 3 is. Oh, excuse me. And so we're going to assume the way we have our coordinate system, we're going to assume that every tick mark is a unit. So I'm going to mark where is X equal to 3. So that's going to give me some usefulness there. Now, you could look at this, and I know this is a polynomial. You'll probably recognize this a little bit later, but they probably find a good reason for us to talk about when they want to talk about what's it equal to. So we want to talk about the limit is equal to 6, and you'll probably say, oh, that does make sense if I'm looking at this notation. Well, let me mark where that is. Limit equals 6. 1, 2, 3, 4, 5, 6. Capital L. And what we're going to want to investigate is we're actually looking at the y-axis and seeing, we're actually going backwards. We're saying, you know, what happens if we choose a y value and we want to get really, really, really close to 3. But we have an idea where we have to be within 0.01 of a unit of 6. And sometimes it's easier for me to say 1/100th of a unit, just in case if you guys are looking at, so let me write that in a different color for you. Sometimes it's easier to say in English this way, but it means the same thing. And so if I'm actually trying to investigate this and I'm looking at the y-axis, I'm going to take my 6 and I want to figure out what happens when I go below 6. So what happens if I want to be within 1/100th of a unit? What is that value? So I take 6 minus 0.01 and I get 5.99. And if I'm trying my best to write where that would be, let me make sure. I'm going to exaggerate this just so that we can all see. I know it's not that much, but let me see if I can. So I know technically on the graph it might not be at that point, but it does help us see. So I'm going to write where the 5.99 is. I'm going to find where that location is on the function. And I will find its corresponding X value. So, you know, we're so used to going the other way, going from the X value, finding the corresponding Y value, but it works both ways. So we're going to be really interested in what is this X value right here. And similarly, we're going to talk about the other way. So as I'm going through this, I'm trying to give you kind of a recipe. Notice where I found my y equals 5.99. I then marked where my x1 was on the corresponding x-axis, just so that you guys can see. And we're going to go the other way. We're going to say, what happens if we're above the 6? So if we take the 6 and we add, oops, I was supposed to color code that. We'll work with it as we go. So if we add 0.001 to 6, we are going to get 6.01. And I am going to exaggerate this a bit for purposes of drawing. We do want to see where these parts are located, but it should be the same distance away the 5.99 is from the 6. So that is where 6.01 is. And we're going to do the same thing. We're going to travel along, see where it hits our function, where is that corresponding y value, and then see where that corresponding x value lands. And that, my friends, I'll call x2. So I'm marking where that is on the x-axis. So what we are really interested in finding out, and I'll try to mark this, I know it's a very, very small picture. We are interested in two distances. We want to know how far is x1 from 3, and I'll write that down. We'll start there. And we'll also want to find out how far is x2 from 3. So we're interested in both of these distances. And I'll color code this for you. So how far is x2? Oh, you had an opinion? Okay. How far is x2 from 3? So kind of keep in mind what I'm looking at as far as distances is I highlighted them on the x-axis, so the distance between x1 and 3, and also the distance between x2 and 3, how far. Now, we should be able to find the upper and lower bounds for the x, and that's what x1 and x2 are considered, so that the function is within 0.10 units of 6. So kind of note this. I'll write this down formally because when we're first starting, it's not bad to speak the language. So we should be able to find these values. So we should be able to find upper, and that's my x2, by the way, and lower, that's x1, bounds for x, so that our function is within 0.01 units from 6. And just remember, why did we choose 0.01? The problem chose this. So the problem specified this. So we're actually looking at function notation a little bit backwards. So if I can kind of remind you, if we're looking at the fact that we do know a y value and we want to find its corresponding x value, there's a little bit of inverse function speak coming along. So if I'm looking at the 5.99, I'm just going to keep everything color coded. So we actually know that the function evaluated at whatever that x value happens to be is 5.99. So we knew the y value. Our job is to find the x value. If that is the case, we can use function notation to help us out. So just kind of recall, they did define the function f of x equals 2x to us. So instead of using f of x notation, f of x1 is the same thing as saying 2 times x1. So all you're doing is replacing x1 as x. There's function notation. And they're telling us that that's supposed to be equal to 5.99. We already knew the y value. So then you're probably saying, oh, well, if I have a mini equation, 2 times x1 equals 5.99, all I have to do is divide both sides by 2, and I should be able to find my x1 value. So you can pull up your TI if we want to. 5.99 divided by 2 is 2.995. You can verify with me if you'd like. And so actually we do now have a value for that x1. That x1 is 2.995. Okay, so we can do this similarly for the other part. We also want the function evaluated at x2. We already know its y value to be 6.01. So our job is to figure out who is that x2 value. Well, we're going to use the same idea with the function notation. They already defined our f of x to be 2x. So if that's the case, instead of writing f of x2, we're going to write 2 times x2, subscripts with the x. And we already know that that's equal to 6.01. So then we have a nice linear equation to solve. We can divide both sides by 2, and we're actually going to get our x2 value. So 6.01 divided by 2, if you want to use your calculator to help you, that's 3.005. So we actually have that x2 value, 3.005. Now that's the main part of this battle, but remember, we were interested in finding the distances. So we wanted the yellow highlighted part and then the teal highlighted parts. So if you're looking at how to figure out distances, it's not 2.995 or it's not 3.005, it's the distance from 3. So if we kind of remember, whenever you're finding distances, your x1 is, if we're going to find that distance, it's 3 take away 2.995 units from 3. Oh, sorry about that. Let me undo that. I was supposed to color code that yellow based on our idea. So I took the 3, I subtracted off the x1 so I could figure out what that distance is. And so if we were to do that, we should get 0.05. Excuse me, there's 2 zeros in there. 0.005. And similarly, we can do the same thing. If we're looking at x2, if we're going to find that teal distance, we take the larger value, so which is 3.005, and we're going to subtract off 3. So that's going to help us find the teal distance. 3.005 minus 3, that's going to be units from 3. And we also find out that that is 0.005 as well. And this shouldn't surprise us. The reason why they're equal, in our case, well, you know, f of x ends up being linear. So we have a uniform distances. So I'll write that down just to kind of as a note. So what we're trying to say is, how close do we make these x1s and x2s? How close do we make it so that we are in 1/100th of the number 6 on the y-axis? We don't have a choice. The distance, no matter what, has to be within 0.005 units from 3. So therefore, we would need to choose x to be within 0.005 units from 3. And I know I'm not necessarily speaking proper math notation. It's easier to write and speak at the same time, but if we're actually saying this properly, if we have 0.005, what do we have? The tenths place, the hundredths place, the thousandths place. So it should be 5 thousandths of a unit away from 3. But it's okay. For higher level math, we can definitely take some liberties here. Now, just in case, all of our functions are not going to be linear, and we may see later on, we might get different distances for these yellow and teal highlighted pieces. If you do get different values, you're going to want to pick the smallest value that you see, because we're trying to get as close as possible to the x. So I'll write that down in a little note with a caution little note. If you have different values or distances, pick the smallest distance. So that is kind of our development of what we're really trying to do. We kind of know some bounds for our y value, and we want to get as close as we can to our particular x value. So it's a little backwards, but you've dealt with some function notation before, so we're going to work with that. So speaking of functions that are not linear, we're going to pull trig back into the front of our minds again. And this is going to help us see a little bit of what we're talking about with the different distances. So a lot of times I try to exaggerate, I try to blow these pictures up a lot larger than what I would if I were just graphing them, because I really want to see what these small values are. So we are looking at the function. It looks like the argument of the limit is, let's see, tangent x, okay. So we're going to have, the first thing I'd like to do for myself, get myself an idea. I'm going to sketch y equals tangent x. And if we want to, if you kind of need some thing to jog your memory, you can go back to our TI. If it does help us see which direction the tangent goes into, we can graph that for ourselves. Although this was on the parent graph, so we should have a little bit of a better idea of what to look at. We can kind of see this on the axis. And a lot of times if I'm looking at the notation, I may play with the x-axis a little bit to make it smaller so I can only look at one period or two periods. And if I can, let's see what we can do. Let's go back and draw this a little bit better. So let's go back. I have a generic axis, and I'm going to really blow this up. I really just want to see one period. Reason being, the way I'm reading the question is they're trying to say if the limit of tangent of x as x approaches pi over 4 is equal to 1, how close must x be to pi over 4 to keep tangent x within 0.2 units of 1? It looks like we're going to be dealing with the function around pi over 4, or x equals pi over 4. So I have a feeling that I can look at the two asymptotes, negative pi over 2 and pi over 2. So that's going to be one period of our tangent function. Now, a lot of times the key to these, if we are trying to figure out these values, if you're drawing these graphs, you can be as accurate as possible. Just take your time. It does pay off a little bit when you're determining who has a bigger distance or a smaller distance. So the next thing I want to play with, if I'm going through this, I'm going to look at what they're trying to tell us, and it's within 0.2 units of 1. So I may mark down, oh, well, we should finish off the tangent graph first. That would be a good idea. So tangent graph crosses the origin. Got really excited. I wanted to show you, but we'll get there. The way I'm seeing it, if I'm looking at the way tangent works, I know pi over 4 was in question. So that might be a good place to mark that. So I could kind of mark where, not pi over 2, pi over 4. So maybe mark where pi over 4 is. And I know that's in between 0 and pi over 2. So if we actually see where that's located, they're trying to tell us that something to do. I do know the way the tangent is if we are looking at the values, the tangent of pi over 4, remind ourselves, should be at 1. So it kind of gives me a little bit of a nice place to help me give myself an accurate graph. I should have about the same idea the other way around, although we don't really have to mark this as much. So this should give me some sort of idea. There we go, a little bit better. I'm a little shaky when it comes to this, but we work on it. You guys have erasers, you can kind of go from there. So we have an idea of our tangent graph. We have an idea of what it looks like at pi over 4. And the question is that we want to figure out within 0.2 units from 1. So it might not be a good, or it might be a good idea to figure out, well, we want to figure out where the limit is 1. So we're going to start with the y-axis. So 0.2, maybe I'll mark it on the right, the left side. Here we go. 0.2 units away from 1 means, let's go back to what we did earlier. We want to get to be above the 1 and below the 1 on the y-axis. So if we're looking at 0.2 units below 1, and I'll mark this, and I'm being exaggerative, it does help us see. I'm going to look at the 1, I'm going to subtract off 0.2 units, and that's going to give me 0.8. And a lot of times if you want to, you could mark, might as well if we're going down there, mark where it's hitting the function, and then mark where it corresponds on the x-axis. So let's see, there we go. And that, my friends, is what we're considering to be the x1. So when we figured out this within 0.2 units away from 1 to be 0.8, we actually were specifying that x, or f of x of 1 was 0.8. So it would be a good idea now to mark where the x1 is on the x-axis. Similarly, we'll do the other way. What happens if we're 0.2 units away from 1, a little higher? So the same distance is away on the y-axis. That would be us adding 0.2 units. So that would give us 1.2. So the math there is not so bad. It's kind of nice. And you notice we have the same distances away from the y. So we're going to go mark where it's located on our function. And once we hit our function, we're going to figure out where that value is. That's x2. So we actually know the value of the function at x2, but now we want to mark where it is on the x-axis. So that's kind of my setup where I want to see what's going on. Now, if I can do this a little bit nicer, let me see if I can mark this. Remember the 0.8, it looks like it's here, and we're marking down. Might It's very subtle, but again, our goals are going to be to figure out what's the distance from the x1 to the pi over 4, and what's the distance from the x2 to the pi over 4. And if we kind of look, or if we have a little more accuracy, we might see that these distances might look a little different. Sometimes it's really hard to see if you're doing this by hand, but what we want to do is we're going to prove this with a little bit of math and algebra, and then we'll really determine. I mean, to me, if I'm looking at it, it looks like they're kind of the same distance away, but I'm suspicious because I know this is not a linear function. So let's see. Next thing I would like to do is find the values of my upper and lower bounds, x1 and x2. So when I do that, I kind of start off with my y values. I'm going to look at the fact that I do know that f of x1 is 0.8 based on the distance they told us to be away from that y value. And also, I can do this simultaneously if I need to. F of x2, they told us that that's equal to 1.2, well, according to what we were able to figure out. So we're going to use our function, our given function, f of x is equal to tangent x. And we're going to rewrite this so that we actually can figure out who this x1 value is. So remember, if we're going to rewrite f of x1, we're actually getting tangent of x1, still equal to 0.8, by the way. And similarly, we can do this simultaneously. We can say tangent of x2 should be equal to 1.2. So our job is to figure out how do we solve for x1 and x2. And so a little bit of trig comes back to haunt us a bit. If we were going to figure this out, in order for us to get the x isolated, we actually have to do this through inverse functions. So we would have to figure out, if we're going to find out who x1 is, it's actually the inverse tangent of 0.8. So all this trig comes back. And similarly with the x2, we're looking at the inverse tangent of 1.2. So let's pull this up on our calculator because I don't know anyone that knows this in their mind. So let's see if we can do that quick computation. And I'd like to point out, we have the tangent x already written in there. Whenever we're playing with our TI, most of the time we are in radians. So let's just make sure what our mode is looking like. And I look at the far left and it does look like the radian part is highlighted, but I know sometimes your calculators are coming from different classes. But I do know since we were talking about pi's over 4, pi over 2, etc., we are in radians. So be real careful with that. That could cause some issues in the WebAssign. So what I'm looking at is the inverse tangent. So if I want to access that, I'm saying second tangent to get that inverse tangent to pop up. And I should be saying 0.8 or just 0.8. I'm going to have a value there. And then I'll do, while I'm here, inverse tangent of 1.2. Let's do that. One more time, 1.2. So we now know those corresponding x values, those upper and lower bounds of x. And for purposes of simplification, I'm always kind of going with either the 4 decimal places or 3 decimal places. So I'll play it safe. And then, we only really need 1 decimal place to see an estimate, but here we actually want to be a little more accurate. So let's go back to our particular values. And remember, we found the inverse tangent. It approximates to 0.6747. Maybe it could be helpful if you want to use 3 decimal places, 0.675. So approximation's okay. I try not to cut off too much because then I'm a little bit off if I'm trying to find distances. So 4 decimal places, 3 decimal places should be good enough. Similarly with x2, the inverse tangent of 1.2, let me make sure it's an approximation. So I'll keep with my notation. There we go. So we have 0.8761 if I'm rounding from my calculator, or if I'm using 3 decimal places, 0.876. So we actually have those x1 and x2 values. So remember, x2 is 0.876 and x1, just so that you guys can see on the graph, it should be 0.675. We know those values. So the very last part is to figure out, we want to find those distances. How far is that yellow distance? How far is that teal distance? So that's the last step on this sort of problem. So we're going to find the distances. And if we find the distances, if I'm kind of speaking in English again, one more time, how far is x1 from pi over 4? Pi over 4. So if I go back, that is our yellow distance. So we're going to have this one, just kind of how far. I highlight that to go with that. So you can kind of play with distances. If I see what they look like on the graph, it looks like the best way I can describe this is I'm looking at pi over 4, subtract off 0.675. But if you're not really having a picture of the x-axis in your mind, if you didn't go through all of this drawing, we could revert back to absolute value, and we can say no matter what, if I put the pi over 4 first, or I put the 0.675 over first, absolute value is always going to spit out my distance. So either way you want to do this, but sometimes it's easier to see the drawing and then you don't have to worry about it. So if I want to find that distance, I'm going to go into my TI. And I already know, since the pi over 4 is larger, I don't have to use the absolute value bars, or I can ignore once I do get the value. It's only, the distances are only supposed to be positive. So pi over 4, oh, there's an extra 0.5 in there, be careful. So if I was looking at this, I have, I'll write it down, write a few decimal places out. Since I use 3 decimal places, I'll write it 0.1104 for now on this one. So we'll go. Okay, so the next thing, same story. We're going to look at the teal distance. So we're going to ask ourselves the question, how far is x2 from pi over 4? And again, that is the teal distance. And if you look at it, you could say, okay, well, the 0.876 is larger than the pi over 4, so we can either write it like that. 0.876 minus pi over 4. Or if we didn't want to bother with figuring out who's bigger or who's smaller, it's the same thing as writing the absolute value. Either way you go, you will still get the same answer. So if we can do this, we'll play with the TI one more time. And I can go the other way. If I were to remember, if you really want to type in absolute value, you can, but we have a little bit of experience. If I said pi over 4, and I subtracted off the 0.876, you notice we do get a negative value, but we know we're talking about distance, so we're going to ignore that negative sign. So I have something about 0.0906. So let's see what we can do there. Go back, update our results. .0906. So if we're going through this, what I want to look at a little bit closer, we're going to notice a few things. So let me see if I can highlight them just so that we see this. If we're trying to decide which one to choose, I want to notice we do have different values one more time. And the reason why we have different values is because we have a nonlinear function. So our job would be to select the smaller distance. And if we were to do this, we want to be careful. We know for sure that it appears that 0.0906 is smaller, the way we see it. And if you scroll back and look at your graph, I was just admiring it, I paused a little bit there. We do technically see that that teal part is a little bit of a smaller distance, and now it's convincing me that that is the smaller distance there. So what I would say on this part is we would need maybe I'll write this off. I can fit this in over here. Therefore, we need X to be within 0.0906 of pi over 4. And so that would be the chosen part. Now I'll let you read into the book. Sometimes if we're looking at finding the answer to this question, sometimes if we were to only take 3 decimal places, you would see the author not apply the proper rounding rules. This is the reason, it's kind of I'll wave my hands over it because I don't want to focus too much on it, but we have to make sure that you don't go past X1 and X2 as far as outside of your required margins. So sometimes if you were to use the proper rounding rules, it throws you outside the particular margin. So be careful on that. Don't spend too much time, in thinking about it or dreaming about it, but you might want to read into it a little bit more if you do go into these a little bit more in depth. So those are 2 examples, or 2 very nice examples to kind of demonstrate our jobs. Is if we know we need to be a certain distance away from the particular y value in question. So I like to point out on the y-axis, the 2 distances are equal, but it also, if it's nonlinear, your yellow and teal distances may not be equal. But everything that you start off with at first, the Y value distances are equal from the particular number. That's based on the criteria of the problem. So practice those. They're not always intuitive. Sometimes, like, it took me a while. I'd like to draw them out. It really makes this work for me. I can see if I can find a Desmos to help you with the discovery of that too. So sometimes maybe the drawing is a little inaccurate. Desmos does make it a little prettier for you. So we'll see what we can do on those pages. Okay, so last part of this section. We're talking about sometimes when you play with limits, there's an issue of you having to figure out that the limit doesn't exist at any point. So there's a couple of times, and I'll say these are the ones we study a little bit more in depth, as which the limit of the function is not going to exist. And the first idea would be, let's say if I had a problem that had a jump. So you guys might have played with this a little bit in calculus, or pre-calculus. So let's say I'm going to make my function, I'll mark where my A is. And let's say I had a function looking, let's say something like this maybe. And then maybe it jumps a little bit and goes this way. A little piecewise for you. And if we're kind of playing around with them, it looks like there's two different pieces. So if we're looking at where our A is, I'm going to approach this in two different ways. If I'm looking at all the X values and I'm coming from the left-hand side, approaching from the left-hand side, all the corresponding Y values to these X values as you get closer and closer to your A, it appears like they're reaching this function evaluated at A at this point. So that it appears that it's reaching, I'll call it limit 1. And so if you're going to approach this with math notation, we can say this: the limit of f of x, we don't even know the equation for that function, as x approaches A. But notice I'm going to mark a little negative sign on that A part. That is equal to L1, whatever that Y value happens to be. It looks like those Y values appear to be getting closer and closer to that limit. And this notation with the little negative sign is speaking that you are approaching A from the left-hand side. And so I like to think about it, it helps me remember negative. If you're coming from the negative sign on a one-dimensional number line, you are coming from the left-hand side. So kind of be careful with that. And similarly, if we were going to play with this direction, if we're coming from the right-hand side, so we're picking all these X values, or looking at all these corresponding Y values, we're coming from the right-hand side, RHS. It appears that those Y values are approaching a different value. And if we were to write this notation, that would be limit of f of x as x approaches A. And this time we're coming from the right-hand side, so you're going to see a positive sign denoting this X value. And that's equal to our second limit, different number. And one more time, because you see that notation, you're approaching A from the right-hand side. Sometimes I like to think about it as the positive side. And these, my friends, when you do see these notations with the plus or the minus signs, these are called one-sided limits. We're not looking at it approaching from each side, we're looking at a single side at a time. Well, when you get that case, looks like the Y values, if you're approaching from the left, are approaching a different value. The Y values as you're approaching from the right are also approaching a different value. since your two limits are not equal, if you were talking about the limit of the function in general, as x approaches a, we say it does not exist. And mathematicians, as you know, they like to abbreviate everything. So you will see us write DNE, does not exist. So be careful when you're going with WebAssign. It has a certain way it like to write that for you. You don't have to use the quotation marks around it, but you will see that notation quite a bit. So another one I want to talk about, whenever you run into a case where you have a vertical asymptote, the little rational functions sometimes come to mind. So let's talk about what's happening at A, and I'll draw a couple of rational functions for you. So let's say we have a vertical asymptote here, and we have a function, maybe it's going here, and maybe another one's coming from the other side. And we're talking about a function as well. We want to play with this. If I'm approaching from the left-hand side, my notation would be the limit as x approaches a with a little negative sign of f of x. And if I really want to look at this, is I'm looking at all these x values and I'm looking at what the corresponding y values are doing. They're getting higher and higher and higher and higher. And it looks like the closer you get to a, the higher the x value is going to be forever and ever. We can refer to this as infinity. And similarly, the other way around, if you are approaching the a from the other direction, it does look like the y values are getting larger and larger and larger. They're not stopping. So the limit as x approaches a from the positive side of f of x is also equal to positive infinity. Now, I'll give you kind of a side note after this, but it does appear that the limits are approaching, the y values are approaching the same limit from either side. So you can say, based on this, the limit as x approaches a of f of x from either side is equal to infinity. They're the same on each side. But I want to kind of give a little bit of a caution, is that a little bit of a note with this. See if I can write this down. Technically, limits don't exist if you're talking about infinity. And the reason why is they don't consider infinity to be a real number. However, we do use this notation where we just write that the answer is infinity. To denote the behavior of the f of x near that x value. So I'll write that down. We use this notation to indicate behavior of f of x near a. So one might just say it's okay. You can write infinity, but be careful. If you're ever studying this a little bit more in depth, we might be able to say it doesn't exist. So I'll let you play with WebAssign, see what they say. So let me kind of go with the other case. As long as they are approaching the same value from either side, a general rule of thumb allows you to write the particular limit. So if I were to see kind of another function, maybe it's a little backwards, reflected a bit or so. And again, if we're talking about coming from the left-hand side, We could say, another case, the limit of f of x as x approaches a from the left-hand side. It looks like the y values, as we are getting closer and closer to a, these x values are making these y values get really, really small, and they actually are approaching negative infinity. And similarly, an approach from the other side, if we're looking at corresponding y values for all these x values as they get closer to a, it looks like they are also getting closer and closer to negative infinity. So you can say if those limits match from the left side and the right side, the limit of f of x as x approaches a is equal to negative infinity. And again, I'll just write, be careful. It's kind of the same situation that we have up here. So maybe I'll put a little asterisk for you, just in case someone is being technical. So we can still use this notation to denote the behavior, but we want to be a little careful about this, that technically limits at infinity don't exist, but we do write that as an answer a lot of times. Kind of strange, huh? All right, so one last thing. Notice that these two examples, with the fact that you end up getting the same left-hand limit and the right-hand limit, they allow you to get the same limit either way. One more time, the question would be, here's where we have to be real careful. What happens if your function approaches a certain value from the left and a different value from the right? So similarly, as we're coming from the left-hand side, the limit of f of x as x approaches a, right, make sure I have that negative sign, is equal to, one time we'll discover this, for every x value, those corresponding y values seem to be getting higher and higher and higher. They're actually approaching positive infinity. And similarly, if we go from the right-hand side, get used to writing this limit notation. We're going to have to write this a lot in the next few sections. The limit of f of x as x approaches a from the positive side or right-hand side. If we look at all those corresponding y values, it appears that they're getting lower and lower and lower forever and ever and ever. So they're actually coming from to go to negative infinity. So here's where we have the issue. The limits don't match. So left-hand and right-hand side limits do not match. Let's say do not match. So we would have to say the limit as x approaches a of f of x, this for sure does not exist because the behavior is different on both sides. So we want to be really careful. Notice here, first few examples where we're playing with infinity, as long as the limits of the left-hand side, limits of the right-hand side match, we're allowed to say the limit is whatever that number is, even though technically it doesn't really exist at infinity, but we'll be quiet about that. But the minute you get something that doesn't match, we have to say it does not exist. So there's nothing we can say about that. So be careful. Go ahead, jump in on your WebAssign and let us know if you need anything. We'll see you next section.